Swayam Prabha. Digital India. Educated India.
Okay. So yeah, after this question, let us move to. We continue with our description of flow through back. So far, in this equation, we have evaluated this term D. So now we want to look at other terms. So the term here is FF. So if it is a laminar flow through a pipe, we know that FF is 16 by RE. So in this case, RE we can define as RE typically dE by mu. In this case, we can replace this till average velocity by superficial velocity. So this will be V naught mu epsilon, where epsilon is your voidage, and then dE we have seen the equation here. So we can use that. So dE will be 4 by 6 times that. So dE we can write as 4 by 6 or 2 by 3. V is fine. Epsilon dP by 1 minus epsilon. Okay. So this is your dE term. Okay. So you can see it again here. So 4 by 6, 2 by 3, or this 6 should be not there. Epsilon dP by 1 minus epsilon. Okay. Okay. So that means Reynolds number will be 2 by 6 rho V naught dP, and then this epsilon cancels out. So we will have this dP by mu. Okay. So for laminar flow, since this is 16 by RE, so now we can write FF as 16 by all these things. So this will be 16 by 4 rho V naught dP, and this denominator will go up, multiplied by 6 mu 1 minus epsilon. Okay. So this is your FF, and by definition here, FF will be equal to what? Okay. So either you can first evaluate this term and then equate it later. So for anything else, anything else will go away. So 24 mu 1 minus mu epsilon by rho V naught dP. Okay. So now, if you look at the previous discussion, we know that this FF can be written as delta P, by 2 rho V square and so on. So we'll do that first. So if you do that, then FF can also write here as delta P by rho V square by 2L by D. Right? But V, so we can further. So this will be delta P. V square will be V naught by epsilon, so that will give you dE again you have, so we'll have to replace that as well. So delta P rho is there, then you have 2L by dE, so dE goes up. So now we can replace this dE. Right? So dE is again what we did here. So dE will be 4 by 6 here, epsilon dP by 1 minus epsilon. Okay. So now you can see if something cancels out. So essentially, you want to equate this side and this side ultimately. Okay. So maybe we should go to the next slide. But can you see if you can cancel anything? You can cancel this 2. You can cancel this. This will be 3. Anything else? No. This will become epsilon q. So if we want to write this, will become delta p epsilon q dp by rho l 3 rho l 1 minus epsilon. Okay. Yeah. So now this term and this term should be equal. So this is what we'll do in the next. Okay. So yeah, we'll have to do some back and forth. 24 mu 1 minus 24 mu 1 minus epsilon by this rho dP. This should be equal to term here delta p epsilon q dP by this 3 rho l 1 minus epsilon. 3 rho l 1 minus epsilon. Okay. So from here you want to find the relationship between delta p with other things. So let's see what cancels out. Rho and rho will cancel out, and we want to keep delta p by L one side. Then take all other things on the other side. So 24 into 3 will be this 24 into 3 will be 72. L we are keeping here, mu will be as it is. And then we have 1 minus epsilon square, because this goes there, and then all these things will come here. I think we are missing something. V squared, what happened to V squared here? Yeah, V naught squared we have missed. Right. Converted this, we will go to some. Okay. So here you have the square. So this you can cancel with this. So in the denominator you have dP squared, this multiplied by this, and then epsilon q. So write epsilon q dP square, and we have missed this term here, so that we will get. Okay. So this is what came from this. What we did was kind of simplified this back bed and then do this to flow through a single pipe with equivalent diameter. And we have come up with this equation, and this gives at least from based on experiments. This analysis actually gives you very nice, very accurate formal dependence of dependence on velocity and porosity and particle size and viscosity, so on. The only thing is when there have been a lot of experiment that has been done on back bed. So the only thing that changes is this coefficient. So this coefficient is from experimentally we have seen people have seen that this is instead of 72, this is 150. So for laminar flow through back bed, we can write for laminar flow through back bed, we can write this delta P by L is 150 mu 1 minus epsilon square Q dP square. And intuitively, you should also try to think this. As you increase, as you want to do more and more fluid through a back bed, you need to apply more. There will be more and more pressure drop. So this is what this equation is saying, and then that variation is linear. Okay. Okay. So next, similarly, when you go to this laminar flow assumption is true if your so typically Reynolds number we have seen how it was. Where is it? Reynolds number, we saw this thing as Reynolds number, but when we define this Reynolds number for backbend, we just remove the coefficient and other things are fine. So then this becomes Reynolds number is rho v naught dp by 1 minus epsilon mu. So if this is how you define the Reynolds number for backbend, you can say E or something. So for Reynolds number less than 10, this flow through backbend is laminar. We'll discuss it. We'll discuss it further. No, this is the relationship that we use. Okay. So now when the flow becomes turbulent, then we need to further. So the basic definition is same. So for friction factor, delta P by L. We saw it here. That part. That means same. So what you can write is as so delta P by L was what? No. So let's write the other way. That will make it easier. Okay. So we know delta P is 2L by D, and rho V square, where you can then write 1 square by epsilon square times friction factor. We can write this. Okay, so this is how friction factor and delta P are related. So now if the flow is turbulent, turbulent, then we expect this friction factor to be independent of, and if the roughness is very high, so if you remember your friction factor versus RE plot, in turbulent regime you have this, and as you increase roughness it becomes this, and at very high roughness it is actually independent of Reynolds number. So this area is kind of straight line here. No, sorry, it's a horizontal line here. So for high roughness, as you increase this side, the roughness was indicated by epsilon. Again, don't be confused with why this. So as you increase the roughness, the friction factor becomes constant, doesn't change in Reynolds number for turbulent flow. So for flow through backbed, I think you can assume the roughness to be very high. So for that case, you can say that this friction factor should be independent of RE. So for that case, you can write delta P equals 2 FF and L by DE, or delta P by L you want to bring here. So 2 FF, and this becomes 1 by DE, and we know that DE can be given as 1 by DE you want, right? So let's rho V naught square by epsilon square. So FF we got here. So 1 by DE, now we can write 2 FF. 1 by DE can be written based on our discussion. We have used it here and factor DE. So 1 by D will be 6 times 1 minus epsilon. 6 1 minus epsilon by 4 epsilon dp. So d you're converting, writing in terms of particle size, and then other things will be it's rho v square by epsilon square. So if you do all the cancellations sector 2, 2, 3, this will become 3f. F, what else is there? there will be rho 1 minus epsilon will be there. Then this will be epsilon cube times dP. Then you have V naught square. So just by this analysis, what we see is that the dependence for turbulent flow. There are two things you can note. One is dependence is with respect to it goes with proportional to V naught square. So if you want to increase the flow rate from 1 to 2 centimeter, 2 meter per second, then you have to you will see 4 times pressure drop increase instead of 2 times for laminar flow. Okay. The other things you can see that, of course, in this regime, since we have it is independent of Reynolds number, so no dependence on viscosity. Okay, so this is the only unknown that remains to be determined, and it has been determined experimentally, and this comes out to be 1.75. 1 minus epsilon by epsilon cube. And then you have rho V naught squared by okay. So this is for turbulent regime, and turbulent regime is defined for REE as we have defined in the previous slide. REE as this, and this is greater than 1000. Approximately 1000. So for so we know based on this discussion pressure drop per unit length for flow for laminar and turbulent flow, and so Argon had these two equations were independently developed by other researchers. Laminar flow relationship was developed by Blake and Pozney, and turbulent one was developed by Burkhan and Plum. Argon, then the question is what we should do in the transient regime. Based on a lot of experiments, it was shown that if you take sum of these two equations, that is, if you that gives you that gives you an equation that is valid for entire range, including the transient region. So you can write 150 mu 1 minus epsilon squared by this is your equation for the laminar region, right? And if you add to this the turbulent one that we just derived here, 1.75 rho 1 minus epsilon by epsilon q dp squared. Okay. Right. So this is how this equation actually covers the entire flow regime. So you can use that to calculate the flow, the pressure drop. So other thing that so this is known as program equation. Yeah. So now what we want to we want to relate this to friction factor. As we have seen in the flow through pipes, if you can relate it to friction factor, you can calculate the energy loss of friction and then use it in your overall energy balance equation. Okay. Before that, I would like to make a comment on the nature of flow through packed bed. In the packed bed, at the same time the flow, so this is your packed bed. Some places, some places the flow can be laminar, and some places the flow could be turbulent because the cross-section area is not same. So somewhere you have more openings, so the velocity may be smaller, and at some places you have smaller openings, so the velocity could be larger, and then so on. So there is so much variation that at the same time your flow could be laminar at one place, could be turbulent at another place. So that if you go into detail, these things will happen. From empirical point of view, this equation works nicely, and it has many applications in this wherever you have this flow through packed bed kind of situation in engineering. Okay, so now as this thing we'll look at how we can relate this to friction factor. So it is essentially the same thing we have been doing. We have been dealing with it. It's nothing new. So if you look at this friction factor, we have in fact done the derivation here. So if you look at this can be good starting point. So let us just write this what we have written, because this is it. You remember that this part is independent of whether you have laminar or turbulent. Okay. So FF we can write as what we got there. Delta T epsilon Q dP 3 rho L 1 minus epsilon square. So 3 rho L 1 minus epsilon V naught square. So let's just rearrange it a little bit. So we can write this as delta P by rho V naught square, and then you have dP by L, and then you have epsilon Q by 1 minus epsilon, and of course you have a factor of 1 by 3. So just for the sake of definition, we do not consider this 1 by 3. So what the way we define F is just delta P by rho V naught square dP by L epsilon Q by minus epsilon. Okay. So if you try to calculate this term if you try to calculate this term from Argon equation, so we know this, all of this. So what you have to do is essentially bring these things together. So delta P by rho V naught square dP by L epsilon Q by minus epsilon. So if you do this arithmetic, you will find that this. Yep. So this gives you friction factor. So if you know the Reynolds number, find the friction factor. Okay. So once you know the friction factor, you can of course find the EF term. EF term is nothing but delta P by rho. So delta P and rho we already know. So if you take other things, delta P by rho, and then this should be just it will come out to be 1 minus epsilon by epsilon Q L by dP, right? So this term, and then you do V naught square, and then you have FF. Okay. So this is your joule per kg term. So if you look at your overall energy balance, that is delta P by rho plus G delta Z plus half U2 squared minus U1 squared plus EF, so WS equals 0. So in this case, for flow through packed bed, it may not be an independent packed bed. If it is just a packed bed, then delta P by L. But if it is connected to some other flow system and you want to do overall energy balance for that system, then you have to use this equation, and for this equation you can find EF as this thing here. So algorithm remains same. You first in this case there is single equation for EF, whether your flow is laminar or turbulent, so that makes life much easier. And other terms you already know. So then you can use the overall energy balance to need to find what kind of fan you want to use, so that you can do, and then so on. So you can do several things. Okay. So with that, I think that is the end of backbed. We'll talk a little bit more about some other few more aspects on about backbed in the next lecture, and then we'll talk about fluidized bed. So with that, let's do this practice problem. So consider this the same problem we did for similar thing that we did in problem 2. So this is water flow through this packed bed. Epsilon is this. You have particle size is given here. The pressure drop through this bed was found to be equal to this 1560 Pascal for water flow rate of 0.1 meter per second. In fact, if you calculate through our equation, you will find that you get this much pressure drop for this thick packed bed. In this case, you have to calculate what will be the friction factor for this flow through the packed bed. Okay, so there are many ways to calculate, and you can use the simplified equation, that is 150 by RE plus 1.75. Remember that in this equation that I have written here, this RE is defined. The factor, numerical factor is not there in that definition of Reynolds. Okay, so you can do this simple calculation, revise what we were just talking about. So with that, thank you for your attention. We will see you in the next lecture.